Hello and welcome to this presentation on electrical and current signature analysis for energy and emissions opportunities in modern electrical systems. We are running through this actually as a practice for my presentation tomorrow for the SMRP Indiana chapter. This will be posted, if I don't get it up the day before, it'll be posted after as our next vlog. My background, lots of stuff having to do with electric machines and all kinds of responsibilities and volunteer stuff for standards and research and being involved in all kinds of unusual things having to do with electric machines. So, pause and read if you wish, but let's move forward. Okay, energy and reliability as it relates to it. Now, I'm going to cover some of the technical portion of it before we get into everything else. But keep in mind, with most KPIs, we can't really, manage what we can't measure. And often some of the new measurement methods or the measurement methods we traditionally attempted to use in reliability and maintenance hinge around things that do not tie to the P&L for a company or to any KPI at the C level. However, energy in particular is most definitely tied to P&L. It can actually have a direct impact, or does have a direct impact, on profitability as well, whether that's square footage in a commercial building or cost per widget in manufacturing. The 2003 study that prompted the Motor Diagnostic and Motor Health newsletter, which had been a motor newsletter from 1996, a study found less than 3% viewed energy as a reliability metric, and when we bounced forward in 2013, that dropped to zero, meaning that nobody was caring that there was a direct tie between energy and every step you take in a reliability program. Every maintenance action you take has an impact. Might be small, might be large, but it has an impact that adds. So we did do some work related to this. The first one I did was in 1995, or was published in 1995, and in that case we had taken an entire plant, a board processing plant, very nasty, horrible environment for all the equipment that was seeing fires and failing equipment and all kinds of nasty stuff. We said, let's go ahead. We're going to put in a what we now call precision maintenance program, and we're going to pay attention to things like belt tension. We're going to put in VFDs where it's called for. We're going to help you streamline the process. We had more productivity while reducing their overall cost by almost 2/3 in energy. And we took the money that was being saved and hired up maintenance staff, trained existing maintenance staff, and used the remainder of the 50% of any energy savings being given back as a budget for making improvements in the plant. We basically funded all the improvements just through the energy costs. Did the same thing as part of a overall program. We were just the motors portion of it, the National Institutes of Health, and observed a reduction in energy by more than 55%. That's tax dollars. So saying at least 14% energy improvement by just applying a maintenance program, not unusual. But let's talk about how we can measure it. So first, let's talk about electrical signature analysis. That's the topic we're covering. Now, it doesn't mean that your vibration program or your any other program doesn't contribute. It's just this is a quick and easy way to measure. So the electric motor system consists of incoming power to the incoming power through the controls, whatever they might be, the motor, the coupling, the load, and the process. Well, electrical signature analysis sees this entire thing all at once. Current signature sees from this point down towards the process itself. Okay, so basically there's certain strengths that electrical signature has, is seeing upstream, certain strengths that current signature has, seeing downstream. Biggest strength for current signature actually is cost to implement and ease. So current signature analysis, this comes from Howard Haynes, the person who first came up with electrical signature analysis in the 1980s. He looked at a combination of voltage and current signature analysis. Power quality is a portion of that. Current signature can see some power quality capabilities depending on the type you use. We're going to talk about a single-phase system, and this, of course, is three-phase of everything. The other benefit you get is walking into a motor control center, you can test a lot of machines all at once. Now, even with when I do wind turbines, when I go through a wind site, 120 turbines, if it's a type that I can test from the base, say a GE tower, I can knock out one every 8 to 12 minutes, depending on the site. That's off very, very quick, considering it takes a half to a full day when you do on-site vibration analysis, meaning that you have to mount everything up tower. But I get to see it all at once, so I can even see the bearings that are hard to get to, say the planet set and everything else. So testing from here, great. Does not mean, one of the downsides is not really seeing physically what's going on at the equipment. So we usually combine this with a walk down. Something that we're running into now with continuous monitoring systems includes missing out on the walk down portion of looking at equipment. So how it works is I use this machine here as the transducer when we're talking about a three-phase machine. So I have a shell that holds the bearing centered, so the rotor sits perfectly centered in the air gap or as close as possible. There's laminations here, there's bars that pass through here. This is a cast aluminum, there's also cast copper, and then of course there is rotor bar style that'll have the bars come out in a ring that's separate from the core. There's other variations you'll see of the core, including venting in it and so on, but these are laminated so that you don't have certain losses in here. These will be thinner and of a higher grade of steel. The core is meant to hold the coils in place. Now, this is a common induction machine. There are new types with different variations of the core. Those can just as easily be tested because our actual transducer is in here, or this portion between the rotor and the stator. The air gap in the machine, that is the transducer, just like a vibration transducer for electrical signature analysis, and as a matter of fact has much the same impact, except we're detecting variations in that air gap both from a radial movement but also a torsional movement, meaning that defects throughout the system have to drive through this, and any type of motion of this rotor inside here, you end up with an unbalanced magnetic pull, and that causes variations in the current as well. So if I have a perfect voltage coming in, I'll have a perfect current going out. If I have the rotor off to one side and I have that unbalanced magnetic pull, I have to consider the inverse square law of fields, in which the pull is many, many times larger, and this is many times lower, so it stands out. It might only be a few thousandths of an inch, but it definitely will appear in the field, and the magnetic field, has a direct relationship to current. Now, if it orbits in there, whether that is perfectly stationary and magnetically orbiting or physically, say a bent shaft, things like that, whereas this might could be from the rotor being off center, or if it's a belted application too much belt tension, or if I have soft foot, the rotor gets pulled off. This tends to occur if I have a lot of broken rotor bars, something going on in the rotor circuit, if it's a wound rotor, or a bent shaft, other conditions. Now I can have a combination of both. The other thing is if I have unbalance, torsional issues, misalignment, and any damage to the rotor, I'll also see those conditions. So I'm seeing a whole lot of stuff requiring us to be able to separate out the frequencies associated with that. Always remember, when we're going through this, we're collecting data off of equipment. So the two types of technologies we're going to talk about include, this is a current signature analyzer, single phase, and this is a three-phase voltage and current electrical signature analyzer, which allows us to look at power and so on. And this particular one here has the ability to make assumptions for power. So both of them can identify energy losses associated with each component in the machine. So we can look at things like bearing friction and stuff like that. A few important things to remember is running speed is the RPM in the nameplate divided by 60. Now that's full load speed. Synchronous speed goes up above that. So if I have a 60 hertz environment, now in a variable frequency drive, that changes, by the way, but 120 times 60 is 7,200. If it's a 4-pole, that would be 1,800. I come up here, and 1,800 divided by 60 would be 30 hertz. Now, if the nameplate, of course, is not going to read that because a motor cannot run at synchronous speed. So it's going to be some value close to that, say 29.7 hertz, that kind of thing, and will vary a little bit based on load. The slip frequency is the synchronous speed minus the running speed divided by the synchronous speed times 60. That gives me a frequency, and then I can either look at twice the slip frequency, or I can go the slip times the number of poles to get pole pass frequency. Both numbers come out identical. Now we're going to be showing everything in decibels. In order to calculate decibels for current, it's 20 times the log 10 of the current of interest divided by the primary current at the line frequency. And then for voltage, it's 10 times the same type of formula. Which actually is very interesting, because that means that as I take a look at it, looking at that logarithmic scale, if I have a defect, my primary current might vary, and any defect currents are going to vary a little bit. Turns out that when I switch over to dB, I get this effect. So this is a misalignment at 62 dB down. So we do everything down from 0. So instead of coming up from the base and say inches per second, acceleration, or anything else, I go primary frequency down to the next frequency. So this is 62 dB down on this machine. Now, because of things varying a little bit when we put a load on it, it will only change by just a little bit. So it got a little less at 86% load. Now, zero load means coupled to the dynamometer but no load. That means it was probably 20 or 25%. So when I get near full load, I don't have that big a difference. Basically, it's not load dependent. What is load dependent is the side-to-side placement of the frequency. So the resolution becomes very, very important. Resolution, sample rate divided by, or basically 1 over the number of seconds that you're collecting data. The Nyquist is a sample rate. Both systems I'll be showing. One is 44 kilohertz and one is 12 kilohertz. So that means that 6 kilohertz for the electrical signature analyzer, and for the current signature analyzer, 22 kilohertz. And going with, say, 120 second or 110 seconds, divided by, this comes out with 0.009 hertz, and that gives me the number of lines. So many hertz divided by that is 2,450,000 lines per second. Yeah. So now if we come up here and we take a look and we say, okay, let's take a look at the differences in time, you can see that the less time you take it, yeah, I've got 2 solid peaks here and everything else. But as I increase, now what we found is as I go beyond this, so if I say did 180 seconds, or basically 3 minutes, I have diminishing returns. So this is about right. This might get in a little tighter. I might go up to that if I'm worrying about, certain things. And this is the same thing again with a defect that didn't exist, and then poof, there's unloaded machine. There's some pole pass right there. Same type of thing here. It's in tight, and I've got pole pass definitely sticks out, but other signatures go away. They basically fall back into the noise. So you see this peak here. Well, it didn't really exist. This is the same data set, just evaluated at different times. So let's say 110 seconds at 0.009 hertz, there's a pole pass frequency, and under the exact same set of data looked at in 30 seconds, you can see the pole pass frequencies blend in with the line frequency. This results in either a false positive or false negative. So let's take a look at another piece of equipment here. So this is one that I just did a couple of weeks ago. It's a dynamometer in a critical application. In this case, it's connected to a set of gearboxes and a load on the other side. But this is the dyno. This is taking one phase of current. Both instruments we used one phase of current. You can see a rotor bar related issue, which turned out when we inspected it be bad brazing, something that should be taken care of, but not the reason we were called there. As we took a look closer, you can also see that there's a bearing issue going on. So we looked at the frequencies associated with the bearings and found out that they had a drive-in bearing issue in particular that was causing problems. And you can see in current signature the exact same type of signature here, and so on. Okay, and again, under higher speed, same thing shows up again. Now, the other thing we get to do with when I have a higher frequency is there's something that we're talking about these days in the engineering end, standards and utility side, is something called supra-harmonics. Supra-harmonics are harmonics that occur from 2 kilohertz out to 150 kilohertz. One of the things you get to look at with a current signature analysis, or this particular device, is the ability to see those harmonics out to 22 kilohertz. These peaks that you see every 2 kilohertz all the way out, those are the drive frequencies. Now, the actual current levels are relatively low, and that's where the debate lies, because some of those peaks are high enough that they will block current flow through shaft brushes while also turning the grease in a bearing into a conductor, meaning that shaft brushes will not resolve the issue, and you end up with the problems, failed bearings due to current shaft currents, regardless. This is a vertical pump. We take a look at this. This was one that was having problems. We were able to identify immediately the reason it was tripping had to do with bearings, the opposite drive-in bearing, and improper settings in the drive, which causes winding stress. You can see that again here. I see that one on an awful lot, and that basically has to do with the settings. So let's get into some of the energy-related stuff. So this one is a fan application, a synchronous fan. We were investigating this because of damage to the belts. And when we took a look at it and we started reading down through everything, of course the belt slip is not a lot. ESA and MCSA is not as affected by varying frequencies during operation. There's filtering that can be done, so this is all accurate. You can see there's actually 3 peaks as this thing's shifting back and forth through its frequency. And here is where we're taking a look at the total energy opportunity and the individual losses as we go through components. So the bearings, you can see inner and outer race have the higher losses on both ends, so that's a bad bearing. Lower here, now if I saw cage and ball as being higher losses but not the inner or outer race, then I would have looked at that as lubrication. Now let's take a look at some stuff with wind turbines to take a look at in a whole system. This is a rotor failure. This technology right now is the only one that detects these up to 12 months before they fail. They're a fatigue fault. Again, there's certain things that we look for in that, and they show up there and also in here. Now, these peaks here, if you're not clear on what those are, that's actually the blade frequency of the tower. So we're able to see the entire system all at once. So if we get into energy consumption, let's take a look at what the opportunities look like there. For instance, this one, you can see I've got my output kilowatts and my input kilowatts. So any losses inside the machine are going to be only up to about 13 kilowatts. And we find that interesting because some companies will claim these massive losses inside a machine. And in reality, when we're looking at critical bearing issues, we're usually talking in terms of watts loss, even in a high-end machine like a 300 kilowatt. A couple other things to keep in mind are things like, it's 0.417 metric tons. That's 2,240 pounds per ton per megawatt hour CO2 when I'm inventorying stuff. When I'm looking at reductions, it's 0.699 metric tons. Now that number should be coming down a little bit because they've just released the last stuff, and I still have to review it to see what the national average is now. 1 metric ton, 2240. Converting kilowatts to horsepower. So kilowatts times 1.341 gives me horsepower, or horsepower to kilowatts is times 0.746. So if I look at this application here, and I have a machine, it's operating 6,000 hours per year, $10 per kilowatt, and 10 cents per kilowatt hour because I'm lazy. And I take a look at this, 193.5 kilowatts, which was that previous machine. This gives me my demand charge, which is $10 per the peak times 12 months. And this one is the usage. So basically comes out to be about $140,000 per year to operate that electric machine. Now, if I take a look at this and I convert it over to megawatt hours, that would be 1161 megawatt hours, which would be an inventory of 484 metric tons of CO2 to run just that one motor per year. So if I look at a facility, let's say we use a 3 megawatt facility. And let's just say we take a look and we say, okay, it's 11,000 metric tons of CO2. Now let's start taking a look at some machines in that facility. So we take a look at a belted application, and we can convert torque readings. I'm going to show you direct kilowatt readings in a minute, but we can convert this just by looking at RPM times the foot-pounds at that point, dividing by 5252, and that gives us, watts or kilowatts. So if we take a look at the beltware associated with that machine, we can see that we've got about $800 worth of beltware. Or we can go directly to a kilowatt reading and read the results off of here. But in either case, if we take that 6,000 hours, say we're running at a constant load, I always use the constant load approach because that seems to end up being a conservative value because there's other things that are going on that use energy that we're not focusing on. So if I turned this in and said, hey, not only we're going to save this much energy, but we're going to reduce by 4.5 tons of CO2, we do the application, we go back and we measure the difference to run the same thing, we're going to see that number, the energy cost actually drops further than that, and this could be as high as 5 or 6 metric tons. So let's take a look at a more complex issue with a belt. And we'll just say those are all frequencies associated with a belt. So we take a look at this one, 109.1 kilowatts coming in. We've got about 12% slip. And we calculate everything out. Now this one is far more severe. So we're looking at a total of about $5,500 or $5,600 almost worth of losses. And because it's so much higher and we're actually losing kilowatts, meaning it's a badly worn out belt and it's slipping heavily in the shivs, so belts and shivs, well, I can cost justify that with this. And then by bringing it back in and then doing a precision belt alignment and proper belt tension, I can reduce 32.3 tons of CO2. Now, if I take a look at a gearbox, and for time's sake, I'm going to move a little faster here. Say I have the bearings and gears have, basically it's a worn system, and it's not that bad. I'm losing about 5.75 horsepower, or 4.26 kilowatts in losses through this gearbox. Going in and making the corrections during an outage, well, in addition to some cost benefit, I can then also report back 24 tons of CO2. This way, if my company has an emissions goal, I can tie my maintenance practice and corrections to that goal. Now, in some cases, I'm not actually looking at a failure yet. I'm looking at the inefficiencies where components within the system are absorbing that energy and will begin to fail. Let's take a look at this particular application. Instead of looking at the exact frequencies, let's take a look at a before and after because the belt needed to be changed anyways. In this case, we were snapping shafts on the system, so they went from, I think it was like 8 D belts or 10 D belts down to 2 V belts, and just a slight change in the shev. So beforehand, the input was 175.6 kilowatts. Afterwards, it dropped down to 163.3, basically almost 12 kilowatts. Now, that's a direct measurement that includes the effects on the system. So I can take that and say 12.5 kilowatts. Take a look, and that's $9,000 worth of energy. Now, I remember the cost associated with this, and we paid for it almost immediately, while also reducing 52.4 tons of CO2 without snapping shafts on the motor anymore, without destroying the bearings, and with basically eliminated, because there were 14 of these machines, eliminated the faults associated with them. So they weren't failing every 6 months anymore. Huge impact cost-wise. The cost avoidance was significant, but management didn't really pay attention to that because cost avoidance isn't on the P&L, but energy sure is, and we were able to show them an immediate, on-the-spot difference, and that had the bigger impact. So let's take a look at a 600 horsepower motor and pump, this 460 on a VFD. They have some very definite alignment issues. I don't know if I have a picture of how awful that is, but they used undersized shims. So we ended up with all kinds of problems, including it taking out the bearings. So overall, bearing issues and some other stuff. These are the bearings again. And when we started taking a look at a few things, we also discovered, because the pump blade frequencies, 2 of them, were very, very high, it turns out when this thing was being assembled, because this is a commissioning test, so this machine's only been in place for a little bit, somebody had dropped and dinged one of the blades on the impeller. And that just little ding caused problems with turbulence, but also caused an energy loss. Turbulence is a huge energy cost. But if we take a look, the bearing cage, there's the peak there, ball, race, and the pump blade, and then the impeller damage, there's the remaining, and you can see about 2.9 kilowatts. And I add all that together, that's about a $5,500 per year, because I have to run this round the clock, and about 33.6 tons of CO2, extra metric tons of CO2 emitted for the application. Now, some of the things I don't do is add together all the actual still. Now, I've provided, there's some links to some US EPA calculators that should still be there. But in any case, if we take a look at the ones that I just showed you, just those first ones, that's about $24,000 and 146 tons. That's just energy savings and the impact just from that handful of items that could be also studied. I mean, I can take a look at other applications, say, hey, if we just do the alignment a little bit better, it can have this impact. So the other thing we get to do is we can use a calculator, such as the US EPA's calculator, and that will give us ideas of what the impacts are in CO2, and you can see it calculated the same thing, 147 metric tons. But what the equivalents are for that, and other ways that would be used to reduce the emissions, because that was the focus. Other areas to continue making improvements would be precision alignment. That's huge. I can increase my losses in the motor by up to 60% with just a standard alignment. But when I do precision alignment, I can drive that way down. Proper lubrication, cleaning, balancing, changing out filters, especially on larger machines. Belts, big deal. That's a huge deal. Load improvements such as air leaks, chiller tubes, and everything else. And, basically anything on the driven equipment. There are some tools that are available through the Department of Energy. These are free tools. You can go in and play with the numbers and see what the impact would be if you do certain things using their modeling tools. Very simple to use. Lots of training available. It's open source. eGrid is used for building your inventory. You can see the address there. The calculator, of course, is a huge deal. Just look it up as the EPA calculator. And let's finish up with one last quick case study. This is on wind power, and this is the sensitivity of an electrical signature or current signature analysis system. So a bearing was replaced on a generator. It's a 1.6-ish megawatt generator, 6-pole. It's a 6330M bearing on the drive end. They decoupled it, replaced the bearing up tower and everything else, did before and after testing. So they went ahead and did the testing. Now the extra peaks relate to stuff having to do with the gearbox, in particular the planetary gear set, and alignment of the main shaft to that to the carrier for it. So there were a few other issues, but we're just going to focus on just the bearings. So the bearing issues showed up primarily in voltage, because generators are voltage signature. And so when we take a look at that from the energy standpoint, now the values are very low in the motor. Now both the high-speed thrust bearing and the bearing on the drive end of the generator popped up in the analysis. So when we add everything together, the total losses between the two bearings, in particular the thrust bearing, which carried the larger value, came out to be about 11 kilowatts. When it was then inspected, it turned out that they had left a spacer out of the coupling, and the result was problems with the thrust bearing. Now, when I had the bearing itself shipped to me, and they had left out the cage, unfortunately, and somebody took all the grease out, thinking it would be better to ship it clean. But let's take a look at what we did find there. So in this case, you can see false Brinelling on the inner race and some false Brinelling on the outer race. A little bit of thrust-related stuff here, and then at least one of the balls dragging because it should have been nice and bright and shiny like that. Oh, there I am, say hi. Now, changing it out, we didn't eliminate all the losses. We just reduced them all the way down because we've reduced the friction, but there's still friction losses. There always has to be. So to suggest that it would be zero would be a bad idea. So about 2.5 kilowatts reduced. Everything dealt with, but the big thing with this generator, when everything was said and done, they weren't going to be back up there replacing everything a short while later. So with that, the time test worked out perfectly, and you guys will get to enjoy the benefit of this. Basically, at this point, this is where I ask for questions. So if you see this posted on LinkedIn or elsewhere and you have questions about this presentation, please feel free